Good morning, everyone. Good morning. Yes, what? I'm also good. What about you? How was your weekend? It was fine. Okay. So, shall we start? Today's topic is the tuple relational calculus. In this way, we are going to we write a relational algebra expression that provides a sequence of the procedures that generates the answer to our query. And that tuple relational calculus, in contrast, is a non-procedure query language. So one is a procedure query language, one is a non-procedure query language that describes the desired information without giving a specific procedure for obtaining that information. And a query in the tuple relational is expressed with the T and the PT. It is a set of all the tuples such that the predicate P is true for the T. And whenever we are using the notation that is TA to denote the tuple of tuple T on the attribute A, so we use TR to denote that tuple T is in relation R. And before we give a formal definition, we reach to the some queries example that is to write for the non-procedural programming language, that is a relational algebra expressions. Now let's take about one example. Find the name, ID, department name, salary for the instructors whose salary is greater than 80,000. This is T, that is for the time period. T, the instructor, that is the file table name. Then T salary, that is greater than 80,000. Now suppose that we want only the ID attribute rather than all the attributes of the instructor relation. So to write this query in the tuple relational calculus, we need to write an expression for a relation to on the schema. So we need only those tuples on the ID such that there is a tuple in the instructor with a salary attribute greater than 80,000. So to express this request, we need the construct that is there exists from the mathematical logic. This is the there exist. Now suppose that we want only the ID attribute rather than all the attributes of the instructor. Now we are using there exist from the mathematical logic. The notation is T, there exists T that belongs to the R relation R of the QT. So there exists a tuple T in the relation R. So there exists a tuple T in relation R such that the predicate QT is true. And using this notation, we can write the query, find the instructor ID for each instructor with a salary greater than 80,000. So there exists with the T instructor where the T ID is equals to SID and its salary is greater than 80,000. And in English, we read the preceding expression as the set of all the tuples T such that there exists a tuple S in a relation instructor for which the attribute of the S and the T are the attributes are equal. That the value of the S for the salary attribute is greater than 80,000. So there exists T with the instructors and what is the output or what is the relation, that is a TID is equals to SID. In salary is greater than 80,000. And tuple variable T is defined on only the T attribute since that there is only the attribute having the condition specified for the T. Therefore, whenever it is using the result, that is the relation on ID. The next query is find the names of all the instructors whose department is in the Watson building. So this query is slightly more complex than the previous queries since it involves two relations. One is an instructor, one is a department. And we shall see it requires that we have two there exist clauses in the tuple relational calculus expression that is connected by the AND sign. So we write the query as T there exists S that is belongs to the instructor with the T name is equals to S name. and there exists U from department, where U dot department or view department name is equals to S department name, and U building equals to Watson. So we are giving three conditions in the AND. So there exists T, that is the instructor, with the T name equals to S name. That is the name of the T, the name field of the T, and is equals to the S of the name. And or there exists department, U department is equals to the S department, and U building equals to Watson. That means the building of the is Watson. This is the name, that is the in-stream, crick, and the goal. So the name of all the instructors whose department is in the Watson building. So tuple variable U is restricted to the department that are located in the Watson building, while tuple variable is restricted to the instructors whose department name matches with that of the tuple variable U. So this figure shows the result of this query. To find the set of all the courses that taught in the fall 2009 semester, that spring 2010 semester, or both. So you use the union operation in the relational algebra, and in the tuple relational calculus we exclude, or we shall need, to there exists clauses connected by the V. There exists a section where course ID is equals to section ID, and semester equals to fall, year equal to 2009, section equals to course ID, semester equals to spring, and the year equals to 2010. So OR is denoted by the V and the AND is denoted by the reverse V or ulta V. So this expression gives us a set of the attribute that is used with the connected name, or that is used with the connected variable, whatever the variable we are using. So that gives the course ID of the tuple for which at least one of the following holds, that the course ID appears in some tuple of the section relation with semester equals to 4 and year equal to 2009. And the course ID appears in some tuple of the relation or the section relation with semester equals to spring and the year equal to 2010. Now, if the same code is offered in both the fall 2009 and the spring 2010 semester, its course ID appears only once in the result because the mathematical definition of a set does not allow the duplicate members. And the result of this query appeared only once, earlier also, that is available within the data. Now, if we want only those course ID values for courses that are offered in both the fall 2009 and the spring 2010 semester, so we need to do so. So change the OR and the AND in the preceding example. This is T, or there exists S section course ID, course ID, semester 4 year 2009, or section course ID, semester spring, and the year equal to 2010. So the result of this query appeared in figure 6.13. Now consider the query, find all the courses taught in the 2004-2009 semester but not in the spring 2010 semester. So the tuple relational calculus expression for this query is similar to the expression that we have seen just seen, except for the use of the note symbol. So T, there exists section, T course ID is equals to the S course ID, and semester equals to 4 and year equal to 2009. This tuple relational calculus expression uses the there exists S with the section that clauses to require that a particular course ID is taught in the fall 2009 semester, and it uses the OR section clause to eliminate those course ID value that appears in some tuple of the section that is taught in the spring 2010 semester. Now the query that we'll consider that uses the implications denoted by the arrow, and the formula P arrow Q means P implies Q. Arrow means implies, and if P is true then Q must be true, and Q is logically equivalent to the P or Q. And the use of implications rather than note or often suggests a more intuitive interpretation of a query in the language. So consider the query that find all the instructors that we have taken all the courses offered in the biology department. So to write this query in the tuple relational calculus, we introduce for instruct or for all instructs construct denoted by the V. Notation is VT, and there exists R QT, where Q is R2 for all the tuples T in relation R. So we write the expression for our query as follows. So T there exists R, and student RID is equals to TID, or there exists U course ID or course department name equals to biology. That implies S takes TID SID and course ID equals to U course ID. So in English, we interpret this expression as set of all the student, that is the ID, such that for a tuple and in the course relation, if the value of U on the attribute department name is biology, then there exists a tuple in the takes relation that concludes or includes the student ID and the course ID. And note that there is a subtly in the above query. If there is no course offered in the biology department, so all the student ID satisfies the condition. And the first line of the query is critical in this case without the condition, because there exists a R that the student ID or R ID is equals to the TID. So if there is no such course that is offered in the biology department, any value of T, including value that are not the student ID, that is in the student relation, that would qualify. So next is a formal definition. So we are now ready for a formal definition. So a tuple relational calculus expression is of the form TPT, where P is a formula and several tuple variable may appear in the formula that is said to be free variable unless it is quantified by the there exists or the. So therefore T instructor E department name equals to S department name. So T is a free variable. So this tuple variable is said to be bound variable. Then a relational or tuple relation formula is built up of the atom. An atom has one of the following forms. So when we talk about the tuple variable formula, that is split up into two parts, that is used in two parts, we can say, or split up into two parts, that is known as atom, that has the following form. So this S belongs to, or there exists R, where S is a tuple variable, R is a relation, that is a table. We do not allow use of the not operator. And X is Y, where S and U are the tuple variables, and X is an attribute on which S is defined, Y is an attribute on which U is defined. In the first case, X is an attribute on which S is defined, Y is an attribute on which U is defined. And this is a comparison operator in between, that may be a less than, that may be a greater than, that may be double equals to, not equals to, greater than equals to. The next part is S is a tuple variable, X is an attribute on which S is defined, and in between there is again the comparison operator with the constant. In the above case, it is using the comparison within the two relations. Now next is a comparison with the constant. So build up the formulas from the atom by using the following rules. That is, an atom is a formula. If P1 is a formula, then so are the P1 is equals to, not P1 is equals to P1. And P1 and the P2 are the formula, then so are the P1 is, or P1 or P2, P1 and P2 or P1 belongs to P2. So this depends on the formula to formula, this depends on the atom to atom. And if PIS is a formula that containing the free tuple variable S and R is a relation, then there exists S that belongs to R, P1S, and S belongs to R, P1S. That are also the formula. So these are the following rule, that is considered with the formula, that is considered with the variable, that is considered with the attribute, with the comparison operator by the using the atoms. And as we could for the we are using the relational algebra, we can write that equivalent expression that are not identical in appearance. And in the tuple relational calculus, these equivalents include the following three rules. So P1 and P2 is equivalent to note of P1 is equals to note of P2. That means we are changing the signs, so we are changing the and with the or. And T belongs to R, where PITI is equivalent to P, that belongs to T1, and P1 is implies P2, that is equivalent to the P1 and the or P1 or P2. And then how it is belong to the safety. So there is one final issue that is to be addressed that generates an infinite relation. So suppose we write the expression T belongs to T instructor. So there are infinitely many tuple that are not in the instructor. And most of these tuple contains value that do not even appear in the database. So clearly we do not wish to allow such expressions to define the restriction of the tuple relation calculus. So we introduce the concept of the domain to a tuple relation formula P. That intuitively the domain of the P denoted with the domain P is that is a set of all the values referenced by the P. That they includes values mentioned in the P itself as well as a value that appears in a tuple of the relation mentioned in the P. Therefore, the domain of P is a set of all the values that appear explicitly in the P or that appears in one or more relation whose name appeared in the P. For example, DOM T instructor T salary is greater than 80,000. That is a set containing 80,000 as well as a set of all the values appears in any attribute of any table that is used in the instructor relation. That means we are using the instructor relation, we are using the instructor table in which TPET is safe for all the values that appears exist at least once in the sense at least once it is used in the appearance of the table. And it is also possible to have a tuple T not in the instructor that contains value that do not appear in the instructor. And the other example of the tuple relation calculus expression that we have written in this section are also the safe. The number of tuple that satisfies the unsafe expression so that the T not T that belongs to instructor could be infinite, where safe expressions are guaranteed to have a finite results. Then expressive power knowledge is not your course. Next part is a domain relation calculus. So till now we have finished with the tuple relation calculus in which we works on the tuples. Then domain, that is we works on the range. So a second form of the relation calculus known as the domain relation calculus uses the domain variable that takes on the values from an attribute. So this takes on a value with an attribute rather than the values on an entire tuple. And the domain relation calculus is closely related to the tuple relation calculus. That is linked with the or closely related means everything is same but there are some syntax, some scenarios are different. And this serves as a theoretical basis of the widely used QBE language, just as a relational algebra serves for the SQL language. Then formal definition. That is, expression in the domain relational calculus is of the form x1, x2 till xn, x1, x2 till xn, where x1, x2 represents a domain variable, p represents a formula in the tuple relational calculus, and atom in the domain calculus has the following forms: x1, x2, xn, where r is a relation in attributes, and x1, x2, xn are the domain variables or the domain constants. And x is compared with the y, that are the domain variable, and that may be comparison may be a less than, that may be greater than, less than equals to, greater than equals to, that may be compared. Then xc, then again the variable is compared with the constant. So we built up the formula from the atom by using the following rules. That atom is the formula. If P1 is a formula, then so not P1 is equals to P1 and P1, and P1 and the P2 are the formula, so are the P1 or P2, P1 and P2, and P1 belongs to P2. And if P1 exists or P1x is the formula in the X, that is the free domain variables. So as a standard, as a shorthand, we are using there exists ABC that belongs to P. Yes, for which each and everything is again the same. Next one is examples of this domain relation calculus that are concluded or that are used over here. Next one is the examples or the example query. Now these examples are based on the domain relation calculus. These are the various examples that is very similar to the tuple relation calculus that we already discussed. So find the instructor ID, name, department name, salary for the instructors whose salary is greater than 80,000. So this is the ID, name, department name, salary for the instructors whose salary is greater than 80,000. That means I and D is instructor and the salary is greater than 80,000. So find all the instructors ID for the instructors whose salary is greater than 80,000. This is N, where exists IDS, then INDS belongs to or is greater than their existing instructor, and salary or S is greater than 80,000. And although the second query appears similar is one that we wrote with the tuple, that wrote for the tuple relation calculus, there's an important difference. And in the tuple relational, when there exists T for some tuple variable S, we can bind it immediately to the relation R or E as that is used with or that belongs to R. However, when we write there exists n in the domain calculus, so n refers not to be a tuple but rather than a domain value, because this works on the domain relation calculus, so this is treated as a domain value, not the tuple value. This n is unconstrained until the subformula INDS that belongs to or that is greater than belongs to instructor constraints n to the instructor name that appears in the instructor relation. So find the next query is find the names of the instructors in the physics department together with the course ID of all the courses that teach. That means we are combining each and every course ID. This is NC. There exists IA, ICASY teaches, or DS, INDS instructor that belongs to T physics. Next, find the set of all the courses that taught in the fall 2009 semester, spring 2010 semester, or both. That means we are combining 3-1, fall 2009 semester, spring 2010 semester, or both. This is C that belongs, so there exists S, CASYBRT, and there exists section, fall Y 2009. Then there exists U, CASYBRT, that belongs to section, and spring and year equals to 2010. So find all the students who have taken all the courses offered in the biology department. This is I and DT student. There exists X, Y, Z, W of course biology, then AB, PRQ that takes C and the depositors. Note that in each case for the tuple relation calculus, if no course are offered in the biology department, that all the students would be in the result. Then this is a safety that we are using. Now next part is a summary of this chapter. We are finished with the domain. We are finished with the tuple relation calculus in the today's class. Next part is a summary. So relational algebra defines a set of the algebraic operation that is used, so that defines that is various combination of the data that combines how it is used or how it is gathered together. So that combines with the result that combines with the output tables. And these expressions can be combined with the positive approach or the negative approach that expresses the desired queries. And the algebra defines the basic operations used within the relational query language. So this is the main aim of the relational query language. So what are the various basic operations that is used within the relational query languages? And the operation that is available in the relational algebra can be divided into basic operations, additional operations that can be expressed in terms of the basic operations, extended operations, some of which add further expressive power to the relational algebra. And the relational algebra is a terse formal language that is inappropriate for the casual users of database systems. And the commercial database systems therefore uses the language with more syntactic language or with the more syntactic syntax that is influenced with the SQL, which is based on the relational algebra. And there are two parts over here. One is tuple relation calculus, one is the domain relation calculus, that are the non-procedural languages that represent the basic power required in the relation query language. And when we talk about the basic relational algebra, this is a procedural language that is equivalent in power to both forms of the relation calculus, when they are restricted to the safe expressions, because these are used with the procedure language that is in same as we use in the tuple and the domain relational calculus. And these are the terms programming languages that are inappropriate with the data, that are inappropriate with the content that is used, or that forms the basis for which it is user-friendly language. That may be a QBE, that may be a catalogs. Then next is the review terms, relational algebra operations, algebra, select, project, union, difference, product, Cartesian product, and rename. So these are the 6 operations that we have studied about. Selection means selecting the rows. Projection means selecting the columns. Union means combining the two relations. Set difference means finding the difference among two tables. So one data is available in one table, another, this data may not be available in another table. So this is find out by the set difference. Then Cartesian product, that is multiplied or combine each and every element of one relation with another relation. Then rename the relation, that is a rename P. Next one is additional operation. So that is a set intersection, natural join, assignment operation, outer join, left outer join, right outer join, full outer join. Then multi-threads, grouping, null value, tuple relation calculus, domain relation calculus, then the safety and the expressive power of the languages. The next one is the practical questions that is used with the computer science department with the relational algebra. Hello, you are able to hear me? Hello. Amity Benjamin, are you able to hear me? Hello. My voice is audible to you?